if this is 5 newtons and this is 2 meters, the magnitude of the torque, which I could write like that or just write like that, is, well, they're perpendicular to each other. So I would just multiply 5 times 2, so 2 meters times 5 newtons. 10 what? What would be the units?
Meters per unit. Meters per units.
Yeah, otherwise known as a Newton meter. If you do put the meters first, because meters are right there. If you want to write meters newtons, that's fine. Just please make sure there's a dot in between. That is a meter newton. That is a millinewton.
Can you write N without the dot?
You can, because capital N doesn't have any prefix meaning. So let's talk about questions here before I talk about fun with units. A 2 kilogram box, like push on it with 5 newtons of force, and let's make that a 3 kilogram box, and the box moves as a displacement. This is my force. My displacement is 2 meters. Flashing back to chapter 7. What is the work that force does on the box? How do you find work?
Force times displacement.
Yeah, so force times displacement, that's force dot displacement. If the force is constant, and they're in the same, and if they're in the same direction, it's just 5 times 2, so it'd be 5 newtons times 2 meters. And what do you get? So here's the fun with the units. If I multiply Newton meters here, so the answer could also be 10 Newton meters. That's perfectly acceptable. If I'm talking about energy or work, that Newton meter is a joule. But if I'm talking about torque, Newton meter is not a joule. It's just a Newton meter. They don't come up with a single word unit for torque. So Newton meter is a joule if dealing with energy or work. Torque, it's just a Newton meter. Years ago, and coincidentally, I happened to be on this topic, and I was driving to school, and this guy was trying to change a tire in the middle of the road. So I stopped to help him, and he was trying to undo the lug nuts. And the device he had was basically you had a hex ending, something like that, so that would fit right over the bolt. But from a side point of view, there was a hinge right here. This is the part that would go onto the nut, and then there was a handle like that. And so he put it on there, and he was trying to turn it like this. Well, one thing, he's trying to apply torque, because that's how you unscrew things. His limit arm was that big. And the force he was applying was purely on friction, so he had to hold on tighter, more tightly, to increase the normal force, to increase the friction. I did manage to give him the one bit of advice of move it over here so that the arm is like that. So now when you push on it, one, normal force, much more effective than friction, and two, you've now increased the moment arm a huge amount. So a practical tip, which probably most people know, but he did not at that moment. And then in class, I was talking about it that day, and some students accused me of having made it up just because we happened to be talking about it, but just an example.
Wait, how do you increase R?
If this is attached to something and I'm rotating like that, R is from the axis of rotation, which is there, to where the force is applied. So my axis of rotation is that bottom. If it's like this, and I'm turning it, my axis of rotation is now this one. Questions? Other questions? We have basically done sort of transliteration about how we've doubled the number of formulas, then we did moment of inertia and torque now. Okay, we've not done centrifugal motion. What is acceleration?
Change in velocity over change of time.
All right. So when does velocity change? What would cause velocity to change?
Change in speed.
Okay. So speed up or slow down. And then the mysterious third one. What's the third thing that would cause velocity to change?
Change in direction.
All right. So we have dealt with, up till now, mathematically, the speeding up and slowing down part. We have not dealt with the change in direction. But that is a critical thing here. So imagine you are taking a curve. So you're on the road. You're taking that curve. What would make that harder to do?
If you were going faster around the curve.
Caleb?
If you were going faster around the curve.
All right, so the faster you're going, the harder it is to make it. And
Not being able to make it harder.
what, steering wheel broken?
I-
Okay, I wasn't thinking about the steering wheel issues. Assuming that your steering wheel works. Which hasn't always been the case for all my cars. So let's say you're doing 20 miles per hour. And you're trying to take the curve. You gonna make it?
Yeah.
there's some great confidence there, and there was a nod over there. Do you think you can do that at 20 miles per hour? Less confident?
Not like that.
What would make it easier?
If it was a
Curve instead of a sharp turn?
Yeah.
All right, so that would be easier than that?
Yeah.
I think most people are in agreement. If you don't drive, something to look forward to. Now, yeah, if you're taking the too sharp of a turn or going too fast, both of those you potentially will start to skid. Because there's a maximum amount of force that's required to keep you in the curve. So these two things that seem to affect the amount of force, well, speed, so the greater the speed, the harder it is. And the tighter the curve, so if R is small, so think about this as part of a circle here. Whatever that radius is of that being a part of the circle, or if we do a much tighter turn, that has a smaller radius. So the smaller the radius, the harder it is. And then, really with not much justification, just sort of, it turns out to be speed squared. This is the formula for centripetal acceleration. We have talked about centripetal. I did the swinging stopper, didn't I? Oh, all the classes in roughly the same area.
So the R from the door, when we're doing the door, the R was radius as well.
Yes. Yes. I guess that's not what I wanted. This is the one I'm gonna use. All right. So as I sling this around, if I release it when it's directly behind me, which way is it gonna go?
Just a regular line, just gonna keep swinging around.
Just keep, so I might hit Sasha.
Probably.
Anyone else?
It's a possibility.
So I did not mention about not hitting Scott. I was doing something similar to this when I was teaching middle school. When I did not hit Scott. I got closer to Scott than I had planned. I did not hit Scott. That was first period. Fourth period rolls around. Student comes into the classroom and said, "Dr. Fox, I heard you hit Scott this morning." No, I did not hit Scott. Scott was prone to overreaction. His parents knew that. I didn't get any parent phone calls from that one. All right, so I let go. So Caleb right now says that Sasha might be hit. Anyone have an alternate theory? So there's the board. I'm swinging it around in that direction. So Caleb's going with, it's going to do that. All right.
Are you gonna let go of the string?
Yeah, I am going to let go of the string. I'm going to try to let go of the string at this point right here. If Sasha is feeling nervous, she can move when I do this. And when I've done this and I've had the possibility of hitting a student, like, to get them to move. Wow. So, I guess everyone's supporting you, Gail. Let's find out.
I would say if you let it go from X, wouldn't it just go straight in that direction?
So you're saying it's gonna go that way?
Yeah. It keeps going in the direction where it was let go from.
I feel like
All right, so now we have another theory.
the speed of their swinging, it has a factor in it though. Like if it's going pretty fast, then it might just go
So I
straight.
got another vote for straight. So you're thinking that it's got this memory of my swinging.
Mhm.
All right. Do we have another?
I was just gonna say I agree with her.
Okay. It's like Cassandra started a movement of 3 people.
I agree with her.
4.
Do it straight.
Let's find out who's right. Place your bets. Alright. Now, I do have to do it slowly enough so that I have control. If I swing it really fast, I am gonna lose some control there, so I'm gonna let go, hopefully when it's right there. Three, two, one. A little bit off. It did sort of go in that direction. I think I let go of it a little bit early and it went that way. But it actually does not have memory of what I was doing. As soon as I let go, motion doesn't have memory, so it has no idea what it did before. All it cares about is at that moment, what forces were acting on it. While I was swinging it, what forces were acting on it?
Tension?
And,
Wait.
yes, those are the two. When I let go, what are the forces acting on it?
Gravity.
Yes, and so that's why it does go down. Newton's first law of motion.
I just said, mm-hmm.
Okay,
An object, isn't it an object?
that's the one. The law of inertia, object wants to keep doing whatever it's doing. It wants to maintain a constant velocity. If the velocity is not constant, what has to be true? If velocity is constant, what do we, oh, sorry.
Acceleration doesn't make constant?
Not necessarily, but you've seen the ballpark and you're thinking about going in. Do you want to change your answer slightly?
Is it displaced? It's not displaced.
That deals with acceleration.
Speed.
It's not a matter if it's constant or not.
There are.
If something is, if the change in velocity is 0, what else is true? Or what is this called? Is it?
Equilibrium?
Yes. And if an object's in equilibrium, what are the other two conditions? There's three things. If this is true, then the other two must be true.
Then your acceleration is in equilibrium?
What is the
Constant.
acceleration is what?
Constant.
No,
Zero.
It's 0.
0. So it's not a matter of acceleration being constant, it's a matter of whether it's 0 or not. So if it's an equilibrium, acceleration is 0, change of velocity is 0, and what's the third one?
Displaced. Sorry.
Think Newton's second law.
Is it position?
Not a position thing, it's a force thing. Oh. Sorry, I misunderstood the hand gesture. The total force,
It's 0.
0. If any one of these is true, the other three are true. Any one of these is a condition for equilibrium. So, if the velocity changes, so if this isn't 0, that can't be 0, that can't be 0. So if the velocity changes, there must be some total force acting on it, a non-zero total force. Once I release it, the only force acting on it is the force due to gravity, which causes it to go downwards. There are no other forces acting on it which would cause it to move left or right. That's part of the lack of memory. It doesn't remember my swing in it at all. So, an object in motion will stay in motion in a straight line unless acted on by some outside force, net outside force, or an object at rest will stay at rest unless acted on by a net outside force. In other words, an object's going to maintain its velocity, whether it's 0 or whatever it is, it's going to maintain the speed and direction unless something causes it to change. Naturally, it doesn't want to. Now, since it wants to go in a straight line, and it doesn't, something must be pulling it back in. Godfather 3 reference. Every time it wants to go out, something just pulls it back in. So something is pulling it inwards. Now, when I had it on the string, what was the force causing it to, what was pulling it back, pulling it inwards, keeping it from going straight? It was mentioned before.
The tension?
Yes, yes, like you mean it.
Tension.
Yes. The tension was pulling it back in. Now that tension acting on it, so if I have the fob, if the fob is right there or the stopper is right there, which way is the tension, at this point, which way is the tension acting? Point with the finger.
Repeat that again?
Which way is the tension acting on this? So it's attached to a string.
If you're still
Oh, so
swinging,
it's that way.
or if you let it go?
No, it's still holding on to it. So
Basically.
I got a couple of people pointing that direction. So it's pointing that way.
No. This way.
The tension's pushing on it.
No, stop. Is it the ball and the string? You wanna find.
So
the
as I'm
first-
swinging this around, the question is, which way is the tension acting on the stopper?
Towards your hand.
Yes, it's acting towards my hand. Tension is along the line of the tight string. So if we look at it from this point of view, the string is tight like that, so the tension has to be along that line. And since this thing, the stopper wants to go in a straight line, the tension is pulling it in. Now, it's not pulling it in enough to spiral into my hand, it's pulling it in just enough to keep it on that path. That tension, which is pulling it in, has a special name, just as that acceleration does.